We've been talking about Lewis structures, and in Lewis theory we represent electrons as dots, and we're just looking at the valence electrons. And obviously after talking about quantum mechanics, we recognize that dots are a drastic oversimplification of electrons, but they're still useful. So what we want to point out here is that electrons are not always shared equally. And you probably have had that experience in real life. What comes to mind first for me is sharing a bed with someone, and somebody gets fewer or less of the blankets than the other person, right? And there's one person who takes the pillows and they take up more space. And yes, you're sharing, but it's not equal, right? So when electrons are shared between two atoms, the sharing is not always equal either. And so when the sharing is unequal, we have a polar covalent bond. What do you think of when you hear the word polar? Yeah, the poles of the Earth, North Pole, South Pole. Yesterday someone said polar bear. Polar Express. The North Pole and the South Pole of the Earth are different. What makes them different? They're opposites in a magnetic field, right? And so a compass points to the North Pole, very close to the North Pole, because it lines up with the magnetic fields of the Earth. So here the word polar means that the two ends of the bond are not the same. But instead of a magnetic field, it's electric. So here we have polar, covalent, the bonds, the electrons are being shared unequally. So the example shown here is with hydrogen fluoride. So here's hydrogen and here's fluorine. And this is representing the electron cloud or the electron density around them. And we see that there's more electron density around the fluorine atom than there is around the hydrogen atom. And this gives rise to a separation of charge. It's not an ionic bond, so it's not a +1 and -1. It's a partial charge, maybe +2, 0.2, and -0.2, or -0.05. It's a small amount, but it's still significant. So we can represent that in a couple of ways. We can use a lowercase Greek delta, which kind of looks like a D with a posture issue. So the fluorine end of this molecule and of this bond will be partially negative. Well, that wasn't very good. You have to forgive me, I'm writing with my finger today. And the other end will be partially positive. So the capital delta meant difference in, final minus initial, and so this lowercase Greek delta is also a difference, but it's a partial charge. We can also indicate this with an arrow. The arrow points to the more negative side of the bond, and then to make it look different than a reaction arrow, put a little plus there. So this is the positive end, and that's the negative end. So here we have hydrogen fluoride molecules. At room temperature, they would be in the gas state in the pure form. And so they're floating around, and they're going to be sort of randomly aligned in space. And if we apply an electric field, positive over here and a negative over here, then we see these molecules line up a lot like the needle on a compass. They'll just swivel around and they'll all line up in the same way. The negative ends of the molecules will be attracted to the positive plate, and the positive ends are attracted to the negative plate. Does that make sense? So I have an analogy, of course, for this. This is one of my favorite ones. I think of electrons as being a lot like, grade school boys, like my son Andrew, kind of squirrely, unpredictable. So what we've got here is the hydrogen house and the fluorine house, and they each have a son that goes out to play, and the kids are playing together. And this cloud around them, the two houses, kind of signifies where are they spending more of their time. Well, how do kids decide whose house to play at? Who's got the best stuff, right? Sometimes it's whose mom is nicer. Or pool, yeah. So we're just going to focus on stuff here and not parenting issues. Over here at Hydrogen's house, they've got a black and white television and a VCR and some old Thomas the Tank Engine tapes. If you're hungry, you'll get a piece of bread. If you're lucky, there'll be some butter on it, and a glass of water. They don't even have an ice machine. Just really basic stuff here. Everything's clean and nice, and mom's really kind and everything, but just not a lot of fun stuff. And then over here at Florian's house, they've got an in-ground pool with a diving board and a slide. They've got the trampoline. They've got all cable channels known to man. They've got every gaming system possible. They have a soda fountain in the kitchen. If you're hungry, Mom will order you whatever kind of pizza you want. Where are they going to spend more time? At Florian's house. Why? It's more attractive, right? So fluorine is more attractive to electrons than hydrogen. So even though these electrons are shared, they're going to spend more time at Florian's house. That make sense? So the degree of attraction, we use the word electronegativity, the ability of an atom to attract electrons to itself in a chemical bond. And so here, you could imagine this is, ranking of people's homes or something. Florian's house is the coolest. And from my description, it'd be hard to, think of anything much cooler, unless maybe you've got ponies to ride too or something. I don't know. Kind of crazy. Here's fluorine. Fluorine is the most electronegative element. And it was arbitrarily assigned a value of 4.0, which reminds me of a grade point scale, right? So 4.0 is the highest, and then everything else was measured relative to that. And so we see that there is a trend, a periodic trend here. So here's another periodic trend. This one is inversely related to atomic size. So remember, atomic size, as you go across a period, the atoms get smaller. It's not what we would expect, but that's what happens. And as the atoms get smaller, the electronegativity gets larger. Going down a column, atoms get larger, electronegativity gets smaller. So these are values for electronegativity. Those might show up in a homework problem, possibly in a worksheet or something, but generally in Chem 1A, you need to know that they exist, but we're not going to really do calculations with them. There are some elements that have the same electronegativity as other elements, like carbon and sulfur, nitrogen and chlorine. So those are there, but we don't need to worry about that for the most part. Do you notice what's missing on this periodic table? The noble gases. The noble gases just really don't make bonds, so we left them off because they mess up the trend. We just left them off. So fluorine, coolest house, okay? So we should be able to do something like this, arrange these elements in order of decreasing electronegativity. This is multiple choice, which makes it a little easier. And we've got the greater than, less than signs here. Come on, pointer. So this is saying that the electronegativity of nitrogen is greater than phosphorus. Decreasing electronegativity means you start with the big one and you decrease as you go through the list, okay? It's so tragic, relatively speaking, when someone gets these questions wrong on a test because they misunderstand what's being asked. They get it exactly backwards. It's like you know the important stuff, but you're missing this one little thing about how a question's asked. So that's why I keep explaining these questions over and over and over again, because I want you to not trip over that. So to do this, we need to find these elements on the periodic table. So here's nitrogen and phosphorus and aluminum and sodium. So 3 of these are in the same period, so those are pretty easy to compare. We've got sodium, aluminum, and phosphorus, which is going to have the highest electronegativity. The phosphorus, because as we go across, elements get smaller and the electronegativity gets larger. The way I think of it is, who's closer to fluorine? It's kind of like in cities or towns where, all the wealthy people tend to live in one area and all the poor people tend to live in one area. And it's not because anyone made them do that, it's just sort of naturally how things work out. So fluorine is, over in the rich neighborhood. And so the closer you are to fluorine, the better the house, right? The more attractive for the kids. And so here's sodium over here, probably not a lot of fun stuff over there. So lower electronegativity. That makes sense? If you wanted to, you could think of this line as the railroad tracks. Anyway, so we're thinking that it's going to be phosphorus, then aluminum, then sodium. But then how does nitrogen fit in? Would be more electronegative, right? So we're looking for nitrogen, phosphorus, aluminum, sodium. Well, it turns out that that's the first one. Yes?
We wouldn't put, sodium, do you remember how you talked about it like a map?
Mm-hmm.
It would go back around, so we wouldn't connect it that way.
No.
Because of size.
Right, we would not connect it around. You could kind of think of over here as being the date line.
Okay.
Yeah, so we're not going to cross the date line. And think about the metals, right? Does a metal gain electrons or lose electrons when it becomes an ion? It loses electrons. So if it should happen to form a bond, a covalent bond, which is kind of weird in the first place, would it be attracted to electrons? It likes to get rid of electrons. So it's good. They're going to have very low electronegativity. Fluorine wants to become a -1 ion. So if you let it, it will take the electrons. Okay? Any other questions about this? The question is, why? Why is it messing up? Okay, so bond polarity. The degree of bond polarity depends on the difference. So the computer's having some sort of an issue, and it's, okay, fixed it. Made the white square. I don't know. Don't ask me. I don't know. Start the thought over again. Degree of bond polarity depends on the difference in electronegativity. So there's degrees of sharing, right? There's completely equal, and there's not sharing at all, and then there's everything in between. And the difference in electronegativity is what helps us decide, well, is this an ionic bond? Is it a pure covalent bond? So over here, when the electronegativity difference is 0 or very small, we say this is a pure or nonpolar covalent bond. I prefer nonpolar because it's more descriptive. We've got polar and nonpolar. In the middle, we have a polar covalent bond where we've got a partial positive charge on one end, partial negative charge on the other end. Electrons are being shared, but not equally. And then at this extreme, we have an ionic bond, electrons transferred, where this one has lost an electron, transferred it to that, and so you have a positive ion and a negative ion. Yes?
An example for the nonpolar, is it where there are the two same elements?
Yes. So a nonpolar bond will always be found when you have 2 atoms of the same element, like fluorine and fluorine. Same attraction, right? So shared equally, or hydrogen and hydrogen. So all those diatomic molecules are going to be like that. You can also have that if you have, copper and sulfur, not copper, carbon and sulfur, they have the same electronegativity, right? Nitrogen and chlorine have the same electronegativity. I managed to remember that from looking at the thing a couple minutes ago. But if the
Those were one of the weird ones.
those are weird, yeah. And you can actually have a little bit of difference here, where it's like it's shared slightly unevenly, but we've decided it's close enough. So we've got these divisions here, and these divisions are arbitrary, but everybody agrees that that's what they're going to be. So if the difference is 0.4 or less, then we call it a nonpolar bond. If it's between 0.4 and 2.0, then it's polar covalent. And if the difference is above 2, we say it's ionic. Okay?
Does the magnitude of the difference in a polar bond matter for, so is a 1.9 difference more significant than a 0.6 difference?
Yes.
Okay.
Yeah. Which dipole moment is how we measure that. You guys are so good at this, leading me into the next topic. So dipole moment is a way of measuring the bond polarity. And we're not going to do anything with dipole moment except hear about what it is, okay? So the dipole moment is given the symbol mu, and that occurs anytime there's a separation of positive and negative charge. So you can have a dipole moment in a bond, you can have a dipole moment in a molecule overall. It's a separation of charge. And so it's quantified as Q times R. R is the distance between these separated charges, and Q is the charge magnitude. So that would be equivalent to the electronegativity difference. So if you have a large electronegativity difference, then the dipole moment is larger. If the electronegativity difference is small, then it's smaller. But size also comes into play there. So it's not quite that simple. A unit for this is the Dubai, not to be confused with the country, Dubai. A Dubai, 3.34 times 10 to the minus 29 coulomb meters. We're not going to use that, but there it is. We've heard about it. So this table down here kind of summarizes this. Electronegativity difference, small, medium, large. Bond types, covalent, polar covalent, or ionic. And here are some examples. So what we need to be able to do is to predict whether a bond is polar, nonpolar, or ionic without pulling out a table of electronegativities and doing subtracting and calculating. Because that is more accurate, but it's tedious. And we just need to have an idea of, is this polar, is this nonpolar? And this becomes important when we talk about intermolecular forces. This is a big deal in organic chemistry. So these are my shorthand, my guidelines. So for the nonpolar bond, I'm going to write nonpolar here. So nonpolar covalent bond, that's going to be two identical nonmetals. So like Cl2, the two atoms are the same. They have the same electronegativity, the difference is 0. There's one other one I want you to know. A carbon-hydrogen bond is considered nonpolar. The difference is 0.4. It's right at that edge, but it's considered nonpolar. That one comes up a lot, and so that's the one I want you to remember. Carbon-hydrogen bond, nonpolar. So if we have a polar covalent bond, that's when we have two different nonmetals. Two different nonmetals. So the example there, hydrogen chloride, both nonmetals, but they're not the same. Now that rule of thumb there is not always correct, but it's correct most of the time. So like the carbon sulfur is not going to get caught by that rule, but in this class we don't have to worry about that. And then for ionic bonds, we've got a metal and a nonmetal. okay? Two of the same element, or carbon and hydrogen, nonpolar bond. Two different nonmetals, polar covalent bond. A metal with nonmetals, ionic bond. That's not too hard. So it's really nice to think of things in terms of, black and white, you're this or you're that, but of course, that's usually not the case. There's all this gray in between. So that's what that continuum was about. And another way of looking at this is percent ionic character. So that's the ratio of the bond's actual dipole moment to the dipole moment it would have if the electron was transferred completely, times 100 to make it a percent. So it's a little disturbing, but no bond is 100% ionic. So electrons actually are never completely transferred. But that's a little issue that we just kind of gloss over and ignore for the most part. This table is this is a graph, showing percent ionic character versus electronegativity difference. And for the purposes of having to draw a line somewhere, we say, well, 50% is the dividing line. If your percent ionic character is over 50%, we're going to call you ionic. And if it's under, it's covalent. It might be polar covalent, but it's under. So what we see up here, all of these guys that are above 50%, they're all a metal and a nonmetal. This guy's really close, hydrogen fluoride, but two nonmetals, and it is under the 50%, so that's covalent bond. And then these guys are smaller, but their electronegativity differences are smaller as well. Okay, so this is something we should be able to do for a test. Not this test, but the next one. Determine whether the bond formed between each pair of atoms is nonpolar covalent. I keep forgetting to change this slide. Nonpolar covalent, polar covalent, or ionic. So between an iodine atom and another iodine atom. It should be nonpolar, right? Because nonpolar means both ends are the same. Because the electrons are attracted equally to these two atoms. They are the same atom. I mean, there's absolutely no difference between them, so why would they be attracted to one or the other? They wouldn't. So the electrons are shared equally. How about between cesium and bromine? Ionic. So we look on the periodic table and we find that cesium is one of the metals. So a metal and a nonmetal is going to be an ionic bond. How about phosphorus and oxygen? Polar covalent. So we could look up the difference, but the rules that I gave you, the shortcut rules, will work for my exam questions. So here, two different nonmetals, I expect you to say that's polar covalent. Any questions?